Hi, I'm Judd Muskat, for those of you who don't know me, and I'm with OSPR, and I introduced myself earlier. Okay, so I actually have a lot of material to cover, so I'm kind of going to gloss over some things. But don't hesitate to ask questions if you don't understand me or if I'm mumbling or something. So you can ask questions, just don't throw stuff at me. Okay, so what am I going to cover here? GIS, Geographic Information Systems. I assume everybody's at least heard the term, whether you're familiar with it or not. Going to go over the basics of GPS, why we use it. I'm going to get into some remote sensing, satellite, airborne, and ground-based remote sensing, and show examples. And then at the very end, I want to bring up IRMA, which is the Common Operational Picture that we have adopted here in California. It's a NOAA product, and it's kind of a joint venture between OSPR and NOAA at this point. Okay, so what is GIS? It's hardware, software, and dedicated personnel to run it. This happens to be Costco Busan. Where's Mac? There's Mac over there. Mac probably remembers. He set us up. Yes. So it involves data collection in the field. We like to do it electronically, but that's not always the case. Using mobile, handheld computers, PDAs, or tablets these days. It includes remote sensing, and it's basically for data management. GIS is an excellent data management tool. And then we're displaying the data, analyzing it, and I'm going to show examples of different kind of map products we come up with. But I needed to insert this slide here. It's not to be rude or anything, but there are certain things that GIS is not, and I have this caveat here unless you're asked to do it by your section leader. But we're not IT support, okay? We're not meeting poster makers. These are common things that we're asked to do, but we have lots to do there. We're not copy makers, okay? We don't print out. We're not there for that. We will do it. We can do it. This is not our role there. And like I said, anything clerical, just there's a documentation unit that can handle all of those types of requests. Okay, so how does GIS work? At the simplest level, a map is composed. Let's see if I can do this. You have point features, you have area features, and you have linear features. Any map you look at is composed as such. AAA mode map, anything. What's unique about a GIS is it ties a specific feature, in this case, this point right here, to a database. Okay, so there's a direct relationship from the feature to the database. Because of that, you can display the data based on attributes. That's the power of GIS, the ability to manipulate on the fly and thus do analysis. Forego my notes because I can't keep track of that. Okay, that's just pretty much what I talked about. Okay, so why have GIS on site? Well, like I said, it's a great data management tool. It gives you the ability to incorporate all these disparate data types that are created at an oil spill. And you can quickly display it and analyze it if data is collected electronically. Doing it by hand, we might have some problems there. Okay, so as of the latest Coast Guard Incident Management Handbook, GIS is usually located with situation. You can see here on their latest, there is a GIS specialist. Well, let's see, at Costco Busan, we had 6 GIS specialists, and at the Deepwater Horizon, there were at least 800, if not more, just spread throughout. The GIS has become firmly entrenched in oil spill response. Oh, and these are pretty much all the units that we support. And there's probably even more that I didn't think about when I put this slide together. So the kinds of products, your typical map products that we'll be putting out are, degree of oiling maps, oiled wildlife, where are the oiled birds captured, where are the dead oiled birds collected, and sampling locations. Pretty much anything with a spatial component, and everything has a spatial component. Booming locations, booming strategies, yes, all kinds of stuff like that. Okay, so here's a typical degree of oiling map. This happens to be Costco Busan. It's kind of hard to tell, but the blue lines are no oil observed, all the way up to red. There's a little bit of red there, and on Alcatraz and Angel Island, those were heavy oiled locations. So it's a quick way to look at a map and you get situational awareness. That's why we're usually part of the situation. So this is going back in time, back into the 90s up at Humboldt Bay. These are live bird locations, live oiled birds, and these were dead oiled birds. So there was a lot of wildlife activity. But you can see just from these maps, you can get a good picture of the spread of the oil, essentially.
Jim, who's doing the quality control on the data that you receive? Are you doing that at your level, or is someone else going to ensure that the data that is used?
Okay, well, in the case of that shoreline oiling data, we require the SCAT teams to be present while we're reducing their data. Yes. Okay. This is just a sampling map. This happens to be the Sassoon Marsh, where that pipeline, somebody was talking about the Kinder Morgan pipeline earlier. And this is just, they put in a whole bunch of monitoring wells, and this is just displaying well based on total petroleum hydrocarbons in the subsurface. Again, the power of GIS. Again, Sassoon Marsh. This was a map we put together just to show the status of the different waterways here. Still needs work all the way to fine, sign off kind of thing. So we use lots of different tools for collecting data. Here's our most basic. This is GPS. These days we use handheld computers. This is even out of date, this picture. We're on to smaller units and soon to be tablets. We use satellite data. That's remote sensing. We use airborne remote sensing. And I'll show some examples. Yeah, GPS receivers, remote sensing, satellite, airborne, and such. Okay, so just a few basics of GPS. Right, satellite-based navigation system, all-weather system. Doesn't matter if it's raining or nighttime or whatever, you're still going to get a GPS signal in your receiver. We're actually better than that these days. We're probably down to about 5 meters in your commercial-grade GPS units. That's this WASP that's pretty much built into everything. Okay, and it requires you need to be in communication with 4 satellites to get an accurate location. Okay, and I have a few slides that kind of depict that why you need 4, not 3. We're dealing in 3 dimensions, not 2. And then just the standards we use, decimal degrees, things like that. Okay, so here's a cartoon of the GPS constellation. There you can see that pretty much the whole planet is covered at any point in time. Just be aware that these satellites are moving, and what is important when you're in the field using a GPS, that you look at the unit and see how many satellites you're in communication with. Because I mentioned 4. 4 is what you want for optimum accuracy. And any GPS unit will tell you how many satellites it's in communication with. So, excuse me, when you first turn on the GPS receiver, it kind of opens up its ears and starts listening. When it makes contact with the first satellite it encounters, it immediately downloads an almanac, which has the position of all the satellites. Right, they're in very precise orbits, and you can know where they are at any point in time. And the computer inside your unit will determine that. Okay, so GPS works on. It's essentially time and distance to give you a location. And what I mean is, satellite's up there and it's constantly broadcasting, right? And omnidirectional. It's just sending out a signal. I'm here, it's this time. I'm here at this time. I'm here at this time. They're all doing that, right? So your receiver is going to pick up that message. It's going to say, oh, there's that satellite. It's that far away. And through that, it calculates your location. So if you were in contact with one satellite, that means your position could be anywhere in a sphere around that one particular satellite. If you're in contact with two satellites, your location is the intersection of those two spheres, right? So you have a circle. Three satellites, there's actually still three places where these circles come together. But four, there's only one place where those four spheres intersect, and that's your precise location on the ground. Right? That's a pretty simple concept, I think. And I really like the way this illustrates it. Yeah, there. Okay, so traditionally for SCAT, the shoreline cleanup assessment technique, which you will be well immersed in as this class progresses, you're probably going to go out and fill out a paper form, right? Well, that paper form has to come back to the command post. Then it has to be input into the GIS. Well, it takes a lot of time, and there's a lot of room for error, especially when you're trying to decipher somebody's handwriting. And I had a situation in Deepwater Horizon where one of my SCAT team leaders happened to have been French-Canadian, and in his excitement, he would write sentences that were partially English and partially French. And I have no knowledge of the French language. And fortunately, we were all staying in the same hotel, and I was able to run up to his room and back on the door and say, what do you really mean here? Okay? But in order to avoid all that, we are trying to get the world to move on to ESCAT, electronically capturing the data in the field. These are some screenshots of a product we use here in California called Pocket SCAT. You have a base map in the background and a series of pull-down menus that mimic your SCAT form that you're all going to look at, and you essentially fill it out in the field. So when you come back to the command post, we can easily download it and incorporate it into the GIS. Saves errors, time, energy, effort, frustration. So here's an example of a map generated from the database portion of Pocket SCAT. Pocket SCAT is for collecting data in the field. When you get back to the command post, the GIS folks use a database program known as SureAssess, which is an MS Access-based program, takes the field data and actually converts it into GIS files, shape files is what we use, the very simplest type of GIS file. Again, this was Dubai Star. I also remember Matt from that one. And that was a bunkering incident here at Anchorage 9. And pretty much the oil just went right to Alameda. The heaviest oil was in there, in that marshy area. Okay, another GPS-based application is our resources at risk aerial transects. We have observers from UC Santa Cruz that they do their pelagic transects. I'm not sure what this was from, this incident here. But anyway, what we get are their track lines. And these dots are individual observations. Okay? Now again, we can display this many different ways. We can display it by specific type or by amount, numbers. So here's one where it was just total numbers of observations. I think this was the Platform A response a few years ago. So we have the ability to display the data however the end user wants to look at it. Okay? And our main client, like I said, is most probably going to be the environmental unit and wildlife operations. Okay, so I'll get into remote sensing here. Look at my water bottle, sorry. I feel like that guy Gudio. Okay, so this is the electromagnetic spectrum, right? It's divided into discrete bands of energy. This is what our eyeballs see, visible light. For oil spill remote sensing, we're dealing with visible down to the UV, into the infrared, and then out here in the microwave where the radars are. Excuse me. So this is my experience from Deepwater Horizon. The most frequently used data sets there were derived from satellite data, airborne synthetic aperture radar, another satellite MODIS, and then we had airborne radar, and then the ocean imaging package, which is a multispectral scanner in the visible and the thermal range. So this is one of the typical images you were seeing on the news, showing the extent of the slick. Satellite data is really good for determining the outline of a slick, but what it doesn't give you are the thickness values within the slick, which is very important to, well, the MSRC. You certainly want to know where the thick oil is so you can be most effective in your skimming. You don't want to be chasing sheens. Oh, and one thing I wanted to point out here, this light brown area, this is sediment coming out of the Mississippi River. And at the beginning, for the first few weeks of the Deepwater Horizon incident, there were tremendous storms inland up north there, and just set torrents of water out the Mississippi, and that actually helped keep the oil offshore. So nature was kind of helping there at the beginning. Okay, this is a typical satellite radar image. This is the mouth to the Golden Gates right there. Radar works on surface roughness. Okay, it's an active sensor. The satellite's up there. Through its antenna, it sends out a burst of energy. Some of that energy is reflected away, and some is bounced back to the satellite. Has to do with surface roughness. So rough urban areas where you have lots of buildings are going to shine real bright. Ocean is going to be a lot darker. Oil on the surface of the ocean is going to suppress the surface, the surface waves, the little ripples, and it's going to create a black effect. Right? The problem with radar, it's great. It sees it's weather independent, time of day independent, but there are many natural phenomena that can mimic the signature of oil on a radar image. I think the next slide is going to just show you the difference between radar microwave and an optical sensor, one that measures reflected light, like that last one I had. Okay, so radar sends out its own energy. That's what it's measuring back. Your optical satellites just are measuring reflected sunlight. So they need clear skies and daylight. Okay, this is the same area that I just showed. I think the tip of Point Reyes is right there. This is the Iconos satellite, which is an optical satellite. And this was taken at 1100 hours. This radar was just several hours before, so you can see there was total cloud cover here, but the radar just, it's like it's not even there. Okay? Has to do with the wavelength of the radar and the size of the water droplets in the clouds. Okay, so again, like I mentioned, there's a lot of things on a radar image that could look like oil. So it could be very, very confusing to look at. I mean, you look at that and you know, is there oil all over the place, or what is it exactly? Dead calm will give the same effect. It's a smooth surface. But there are some times when it's clearly evident that you're looking at something that is not a natural phenomenon. And this is the case here. This happens to be a vessel that was coming out of Long Beach, leaving us, that's 18 miles worth of slick. So at top speed, that's at least an hour of deck washing or bilge pumping or whatever it is they were doing there. We don't know for sure that that's oil because nobody took a sample of it, but you can make sort of a guess. They're saying they're leaving us something here, some little present. And then being a GIS person, of course, I just followed it down and hooks right into the shipping lanes. Okay, so because of all those false positives that are that can occur in radar, OSPR we were looking for a system that can positively identify oil. Radar is great for a synoptic picture. You can cover thousands of square miles, in an instant, just like that. But like I said, you don't really know what it is unless like something like that ship image that I showed you here. So anyway, we got together with Dr. Jan Svikovsky at Ocean Imaging and started doing some experimentation with his multispectral camera. Jan was under contract to Fish and Game to map kelp for the marine region. And we decided, hey, let's just take that camera and start looking at oil. And there's lots of scientific literature talking about sensing oil slicks. Okay, so this was not novel. It was just, what's different about this is we used a small portable sensor that can be used in an aircraft of opportunity rather than the more sophisticated systems that are out there, specifically the Northern Europeans, the Bonn Agreement. They have dedicated aircraft, multi-million-dollar aircraft that are dedicated for remote sensing and have all these sensors on board. But being the small state of California and these days being essentially broke, we thought this was the way to go. So here it's mounted in one of our Partnavia observer aircraft, and here you can see we tied it onto the struts of a helicopter. So we went out to Santa Barbara Channel where all those natural seeps are. We saw immediately that we can tell kelp from sediment, from oil. Okay, we kind of knew that was going to happen. This was a proof of concept. We did that. Then we went out to the OMSET test tank, actually many times, and started working on thickness variations. I guess I don't have the slide up here that I was talking about, but as we looked at the oil slicks in the various channels, when I say multispectral, it means you can look at different bands of energy simultaneously. Okay, so we were looking at 4. And we noticed that as we looked at the slick in the 4 different bands, the shape of it sort of changed. And we related that to thickness values, okay? That's when we went out to OMSET, and at this point in time, the feds jumped in and started funding us too. We went out, set out a bunch of targets with known thicknesses of oil, did our imaging, there's the sensor there, and came up with algorithms for determining thickness values within the slick. We later added a thermal camera and an IMU, which is an inertial motion unit that tracks the pitch and roll, the yaw of the aircraft, so we can mosaic. We can do that pretty much all in real time. The first time it was deployed, we were still experimental. This was the Costco Busan spill. So this was not used for any operational decisions at this point in time. It was strictly experiment, but we quickly noticed we could pick out recoverable oil, which would be the red here, versus sheen. And if you look close, I don't know if you can see, but there's all the response vessels there. And some of them, you can see they've got oil in their boom, but they're working in an area that does not have a lot of oil, and they basically did not have this perspective. Okay, if they're looking from from the deck of their boat, they can't see very much at all. They probably had a helicopter spotter, but he's only going like 500 to 1,000 feet. This image was, I think we were 10,000 feet taking that. This is platform A, where we again use this sensor system. What it was, platform A here. That's the one that Jordan mentioned at the beginning, the one that blew out in 1969. Well, they had a little burp back here in, I forget what year this was, 2008 or 10 or something. What this sensor was really useful for there was determining endpoints. When is there no more recoverable oil? When can you call off the on-water operations? And it was excellent for that. I want to point out these vectors here. We just had an assignment, and you talked about HF radar, high frequency radar. That gives you surface currents. And if you look, I want to show that. Early in the morning, we had our aircraft go out with a warden, and they just kind of flew the perimeter of the slick at that time without the sensor package. Several hours later, with the sensor package, they imaged the slick. You can see it moved southeast, pretty much exactly the way the HF radar vector is showing. Yes?
So when you deploy the spectrometer, do you it seems like sometimes you'll use aircraft that aren't your aircraft, like a helicopter or something. Is something you like load it into a van and you drive it somewhere?
Fly it somewhere.
Fly it somewhere.
You can stick it in a big gym bag, duffel bag kind of thing. Right, in the Gulf of Mexico, it was used extensively in the Deepwater Horizon, and it was on board a NOAA aircraft there, Twin Otter. So you just need some kind of camera bay, hole in the fuselage, and you find a mounting plate and get the electrical wired up, and you're good to go. Okay, so this image here, this map, shows the outline of the slick based on radar data. Okay, like I said, radar is great for determining the footprint of the entire slick, but what it can't get you are these thickness values within. So this is the airborne remote sensing laid over the radar, and here you can see there was thick oil blending out to sheen there. There, that's better view of that. HF radar. This is your HF radar antenna. It's ground-based, not satellite, not aircraft. They're installations all along the coast of California here. So this is pretty much the coverage at any given point in time. It's not always like that. It just depends on, well, these days it actually depends if the sensors are turned on or not, because there's a big funding issue. Okay? They're all operated by academic institutions and others, such time Marine Labs. BARI, I think, operates them. It was funded by the state of California. Some $20 million was spent to install all of these, but there was no provision for ongoing funding. So they're operating literally on a shoestring right now. Graduate students, I should say. Graduate students. Anyway, it's very simple. You can fit this in a phone booth. I mean, it's just a tiny thing and blasts out. The microwave energy goes out, hits the wave tops, and then bounces back. And that's essentially what you're measuring, the direction of the swells. And just for your information, these are surface currents. So only talking about top 6 inches to a foot. What's going on beyond that could be anything. Our oceans are very complex, and you'll get a dose of oceanography in this class. Okay, so this is just a printout from the IRMA package showing the HF radar around here, around San Francisco Bay, whenever I did this. Okay, so I'll get into IRMA here. Like I said, it's developed by NOAA and the University of New Hampshire. Designed as a common operational picture. And I'll just say a little bit about common operational pictures. We had a workshop last week. It's our biannual OSPR Chevron technology workshop. And there were at least 3 different vendors displaying common operational pictures, software to generate a view for everyone to see. What they all had in common was nothing. What we need are standards for symbology, so that are platform independent. So when somebody walks into a command post, looks at the situation board, they know immediately what they're looking at. They don't have to go and say, well, what are these red dots? What are these green dots? Kind of thing. And that's something I hope to work on with NOAA here, to develop those standards for display in a common operational picture. Yeah, so at Deepwater Horizon, a situation developed where NOAA brought out IRMA, and at the same time, BP brought out their viewer, or their common operational picture. And of course, they insisted on using theirs, and the Coast Guard was using IRMA, and the bottom line was neither one of them told the entire picture, because some data was going one way and some data was going the other. So in order to avoid that situation here in California, we've adopted the NOAA COP, IRMA. And we put a lot of effort into it. And I probably have plenty of time, so I can show you some of that. Yeah, so that's us. Okay, so if there aren't any questions, I'll jump into IRMA. How am I doing?
17 minutes.
Okay. Yeah, because that means I gotta improvise now.